Hello ladies and gentlemen, welcome to my video. Here we would like to solve an integration problem of a series of the functions. It looks similar to some of my previous video before. However, for this question today, we have an additional integration in the questions. The first step is to rewrite the series of functions into sum from k equals to 0 until infinities. Q can be rewrite as integral 0 to 1 sum of k equals to 0 until infinity x power k divided by k plus 2 k factorial and then dx. From now we will leave the equation Q here and we come back later. Based on Taylor series, e power x equals to 1 plus x power 2 divided by 2 factorial plus x power 3 divided by 3 factorial and so on can be rewrite as sum of k equals to 0 until infinity x power k divided by k factorial equals to e power x. Then multiply x to both sides. The right hand side become x multiply e power x, while the left hand side the x power k become x power k plus 1. Define L equals to integral 0 to t of the left hand side dx, where t is a dummy variable. Because integration is for dx, nothing to do with k, we can swap the integration and the summations. And then the summation is still there. Integration of x power k plus 1 become x power k plus 2 divided by k plus 2. K factorial is still there. Put in x equals to t and x equal to 0. We have L equals to sum k equals to 0 until infinity t power k plus 2 divided by k plus 2 k factorial. And then minus 0. The minus 0 can be eliminated. T is a dummy variable. We can change back to x. Meanwhile, define R equals to integral 0 to t x multiply e power x dx, where L is equals to R. Solve R using integration by part DI table. First row is positive, choose x for d, e power x for I. Second row is negative, d equals to 1, I equals to e power x. Third row is positive, d equals to 0, I equals to e power x. We obtain R equals to x multiply e power x minus e power x. Putting x equal to t and 0, we have R equals to e power t multiply t minus 1 and then plus 1. Again, t is dummy variable, we can change it to x. Based on what we derived before, we can tell that L is equal to R. Let's write down the L that we found equals to the R that we found. And then let's write down the original equation Q. As we can see, the left hand side L is similar to the summation part of the question Q. It will be exactly the same once we divide the L with x squared, which means we also need to divide the R with the x squared as well. So divide the right hand side with x squared. For left hand side, once we divide with x squared, the x power k plus 2 becomes just x power k. Therefore, Q equals to integral 0 to 1 e power x multiply x minus 1 and then plus 1 divided by x squared dx. This is a good news because no more summation, no more k. This is something simple, which is integral 0 to 1. Differential of u divided by v over dx and then dx, where u equals to e power x minus 1 and v equals to x, which is equals to e power x minus 1 divided by x for x equals to 0 and 1. Putting x equals to 1, we have e power 1 minus 1 minus L0, where L0 is limit x goes to 0 for e power x minus 1 divided by x. Put in x equal to 0, we have 0 divided by 0. Apply L'Hopital rules. It becomes limit x goes to 0 e power x, which is e power 0, which is equals to 1. Therefore, Q equals to e minus 1 minus 1. That brings us to the conclusion of this video. The final answer of this question is equals to e minus 2. Thank you for watching this video until the end. Please support my channel, subscribe, give a like and share my video with others. See you tomorrow for another video. Bye bye.